start questions you have. So I'm not rushing to fill in this table. I'm rushing to keep getting you closer to filling in this table. So Chloe. Okay. How many of you struggled with remembering? Oh, okay. Formal charge. All right. What is a structure that you know? Like I'm guessing that everyone drew SiCl4 correctly, right? Okay. So tell me, uh, SiCl4, what am I drawing? Si. What's the step that we need to make sure we're including? Counting electrons, right? Okay, so we're counting electrons. How many does silicon have? 4. Each chlorine has 7, and there's 4 chlorines. So we have 32 electrons, right? Silicon goes in the middle. Cl, 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 right? And then, so how many electrons is that total? 8. So then 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, plus the original 8 is 32. Yeah? I'm guessing all of you successfully drew that, right? That was an easy one. Okay. What is formal charge? Does anyone remember at all? No one? Okay. All right. Formal charge is when you figure out how many valence electrons each atom contributes to the structure. Okay. So silicon contributes 4 each, right? Or 4 because there's only one silicon. And then each chlorine contributes 7, right? Are you with me there? Okay. Then what you do is you look at the electrons surrounding each atom. If there is a line, you only count it as 1 for that particular atom, because the idea is that each line represents 2, but they're sharing. So we're assigning one of them to one atom and one of them to the other. Does that make sense? Okay. So silicon contributes 4 electrons, right? So it contributes 4 valence electrons. And how many lines does it have on it? 4. So we're going to count that as how many? 4. So we're going to subtract, and that's going to be 0. So silicon's formal charge is 0. Okay. How many valence electrons does each chlorine offer? 7. Okay. We're going to count each dot as an electron. 1, 2, 3, 4, 5, 6, and then the bond is another 1, so that's 7. That means chlorine's formal charge is also 0, right? 7 minus 7. Okay. Would all the chlorines be 0? Okay, in this structure, yes. All the chlorines would be 0. Okay. That's the ideal structure. The ideal Lewis structure, and this is what formal charge is for. Our formal charge is for having a way to determine if you draw the structure differently than one of your peers, is there a better structure? Or are they resonance structures? Okay. And the way you determine if it's a better structure is by looking at formal charge. If all the formal charges are equal to 0, that's the better structure. Okay. If the formal charges are not equal to 0, then the atoms that are more electronegative should have a more negative formal charge. Okay? So if the formal charges do not all equal 0 in the molecule, then the more electronegative atom should have a more negative formal charge. So if you draw multiple structures, for example, and like we know fluorine is the most electronegative atom, right? Well, if you draw multiple structures and it turns out that in one of your structures, fluorine's a +1, but in a different structure, it's a -1, you want to choose the structure where it's a -1 because it's the most electronegative atom and that formal charge would be a negative value. Okay. So here's what I want you to do now. Go through and hopefully go through your structures and assign formal charges. Did any of you have different structures than any of your group members for any of these? Or did you all have the same? Okay. If for some reason you have different structures than each other, assign formal charges and see if one structure would be better than the other. Okay, so go ahead, take a couple minutes there. The first structure, okay? You should have had 24 valence electrons, correct? Okay, and then what's the challenge? Once you draw 24 valence electrons, what does it become obvious that you're going to need to do? You're going to need to make a double bond. The question is, do you make it with the oxygen or do you make it with one of the chlorines? And how do you decide? And the answer to that question is in formal charges, okay? The formal charges tell you where to put the double bond. Where did you decide to put the double bond? Oxygen. Why? Because oxygen has 6 valence electrons, and if you put the double bond on oxygen, what is its formal charge? 0. And so are all the chlorines, right? Okay, so if we look at that, right, here's where you would have stopped, correct? Like you counted, you drew out your 24, right? And then you had to decide where are you going to put the double bond. Well, I want you to look right now. Chlorine has a formal charge of 0 right now, correct? So does this chlorine. What is the formal charge on oxygen right now? It's -1, right? Because it's 6 minus 7 is 1, correct? Okay. And what's the formal charge on carbon right now? +1, okay, because it has 4 valence electrons and it's only showing 3, okay? So realistically, that's why you're going to erase a shared pair, hold on a sec, on oxygen and convert it to an unshared pair, or erase an unshared pair, convert it to a shared pair, right? Opposite of what I said. Because what is the formal charge on oxygen now? 0. What is the formal charge on carbon now? 0. So do you see that by drawing this structure, it gets all your formal charges to 0? That is why this is the better preferred structure, okay? So it confirms through formal charge what the structures should be, okay? All right. How many valence electrons do you have for SF2? That's the next one, right? How many valence? 20. Okay. So that should have looked like, and I erased a dot accident. Oops, it's supposed to be black. That should have looked like that, right? Okay. What are the formal charges? That's gonna bug me. What are the formal charges on fluorine? 0, because 7 minus 7, right? So each one is 0. And what's the formal charge on sulfur? Also 0, because sulfur has 6 valence electrons, then 1, 2, 3, 4, 5, 6. Okay, good. All right. CO3 2 minus. How many valence electrons should you have? 24. Carbon has how many? 4. Each oxygen has 6. And then that's going to get you up to 22. Where are the extra 2 coming from? The charge. Okay. So you should have gotten, oops. I'd have erased that. You should have gotten this far, correct? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So what are we going to have to do? What's that? Well, are we done? No, because what's wrong? Carbon doesn't have 8, it has 6, okay? Does it matter where so what are we gonna have to do? Because we're out of electrons. We're gonna have to make a double bond, okay? Does it matter where? No, it does not matter where, okay? I'm gonna put it over here on the right. Did any of you put it on the left? Raise your hand if you put it on the left. Raise your hand if you put it in the middle. Okay. Are any of us wrong? No. In fact, so I'm going to draw my brackets like you were saying. Okay. In fact, if we could draw this 3 different ways and all be correct, what does that mean? What are those called? Resonance structures. Do you remember? Resonance structures are equally valid structures, okay? And here's what I'm going to tell you. So and we should maybe like go to a new page, okay? Let's look at this. So for example, CO3 2 minus, okay? You could have drawn it like this. Okay. You could have drawn it like this. And you could have drawn it like I did, which was like that. And in fact, these are all equally valid, and they are resonance structures. Because if we figure out, well, we'll look at it in a minute, but when we do formal charges, I'll explain why they're equally valid, okay? But here's the thing. In reality, the carbonate ion exists in these 3 forms all at once and not at all. Hear what I just said. The carbonate ion exists in these 3 forms all at once and not at all. Meaning it is a hybrid of these. This double bond bops around. It's not in any one of these locations ever. It's in all of these locations simultaneously. Okay? And this gets considered a bond and a third. Like that's how, like instead of thinking like, oh, single, single, double, it's like single bonds, and then this double bond bops around to three possible places. So it's considered a bond and a third because that double bond is not consistently in one place. Okay? And that's what resonance structures are. Resonance structures are equally valid structures that exist simultaneously. Okay? And realistically, if you have carbonate ion, you have all of these at the same time, right? And then within each ion, that double bond is bopping around because that double bond reflects electrons and electrons repel each other, right? Like, so realistically, they're constantly moving to try to find a good place to be. And is there ever a great place to be? No, that's why they're constantly moving. Okay, so that double bond moves. And that's why it's considered a bond and a third in terms of type of bond. Okay, now let's talk formal charges on the one I drew up here. Okay, what's the formal charge on carbon? 0. What's the formal charge on this oxygen? -1, because 6 minus 7 is -1. What about this one? -1. What about this one? 0. Okay, now what's the only thing that's going to change if I move where the double bond is? The formal charge of each specific oxygen. But realistically, like if I put the double bond here, this is going to be 0 and these two will be -1. If I put the double bond here, these will be 0. This will be 0. These two will be -1. Am I overall changing the like collection of formal charges? If I have -1, -1, 0, 0, is that changing at all with those different structures? No, that's why they're resonance structures, because it's just shuffling the formal charges around. It's not actually changing them. Okay? It's just moving where they are in the drawing. Okay? So, all right, good. How'd KrF2 go? How many valence electrons? I don't have 24. How many does krypton have? 8. How many does fluorine have? 7. So that's 14 plus 8 is 22. This is a molecule, and so this is a great example of follow the steps for how to draw Lewis structures that we talked about the other day. I will tell you right now, you will get every structure right if you follow the steps that we discussed. Step 1, count your valence electrons. Okay, now let's talk about the next steps, but this is a great one that you could easily overthink because if you're not following the steps, you're trying to make sense out of something that looks confusing. How many of you found this structure to be difficult? Okay. But like you always want to know the right answer. I'm telling you, you'll get the right answer if you follow the steps. Okay. What's the next step? So count valence electrons. Boom, 22. What's the next step? Place the least electronegative atom in the center. Who is less electronegative, krypton or fluorine? Definitely krypton. Why? We could use a couple of different rationales for this. Name me one. It's a noble gas, which means what? Yeah, it doesn't really want more electrons anyway. Do you think it's going to be a very good tug of war player? No. It's like, dude, I have everything. They're like making me play. Okay? That's who that is. That's like me in gym class in high school. Like, okay, I'll stand on the volleyball court, but if you think I'm going to actually hit a ball, I'm not. Okay? Uh, that's that's the noble gases. All right. What do we know about fluorine?
I was gonna say, this is,
I don't know. Go ahead.
Krypton has more shows.
Yeah, it is also significantly further down. So electronegativity wise, it's not going to have as good of a pull because it's farther from the nucleus. However, the fact that it's a noble gas, like even if we were looking at neon, would would also override that because it doesn't need to win tug of war. What do we know about fluorine? What? Yeah, so talk to me about electronegativity. What do we know about fluorine? You guys, fluorine is like the world champion. Like it has the tug of war belt. Okay? Like gold belt champion has dominated at tug of war its entire life. No one can take fluorine down. Okay? I want you to picture fluorine wearing like a big gold like wrestling belt. Okay? Are you picturing it? That like, and it's in the family, like they're all good wrestlers. But who's the best wrestler in the halogen family? Fluorine. Okay, that little kid, I'm saying it's little because it's the smallest halogen. That little one's the scrappiest, right? It's wearing the belt. Okay, it's pulling those electrons, right? Okay, so anytime we're looking at a molecule where fluorine is one of the atoms, guess who's probably not going in the middle? Fluorine. Okay. So we're going to put krypton in the middle. So put krypton in the middle. And then what's the next step? Connect the other atoms to the central atom with a single solid line with a shared pair. So krypton in the middle. I am krypton. Okay. Fluorine, fluorine. Right? So now we've accounted for 4 electrons. Okay. What is the next step? Place unshared pairs around the outer atoms until they have a complete octet. Who are outer atoms? Fluorine. How many dots is each fluorine going to get? 6. So dot it up. Okay. 2, 4, 6. 2, 4, 6. That's 12 plus 4 is 16, right? What is the next step? What is the next step? Place extra electrons on the central atom. Do you have extra electrons? How many? Where are you putting them? On the krypton. Are you questioning it? Are you wondering why? Probably. But what have you been told to do for drawing every Lewis structure if you want to get it right? Follow the steps. Did the steps say, now question this method? No. The step said, put the extra electrons on the central atom. Okay? So you should have done that. Right? Because now 2, 4, 6, 8, 2, 4, 6, 8, that's 16, 18, 20, 22. My 22 electrons are accounted for. you might be thinking, ah, right? Did any of you draw that and think, nah? Okay. But it's correct. I did walk around and see some double bonds. Let me tell you what the problem is with double bonds. Double bonds are something you draw when you don't have enough electrons. That's actually the opposite problem that we have right now. The problem we have right now is we have more than enough. That's what's making you uncomfortable, is that you have more than enough electrons. Okay? And you might be wondering, well, why? Okay? Well, you already told me why. What does krypton have? A full octet. So realistically, here's krypton, right? Here's what krypton's doing. It's taking one of these and one of these and bonding. So how many electrons do you see left on krypton? 6. So does that explain where those 3 pairs came from? It's basically sharing unshared pairs. Okay? And krypton does that. So does xenon. Like, these are actually chemicals that exist. Okay? So it, and part of the reason is because those are larger atoms. So the nucleus, doesn't have as strong of a hold on those valence electrons. So they are kind of willing, because realistically, when we're talking about bonding, you guys, oops, that says K, not KR, sorry. When we're talking about bonding, what you're really talking about is orbitals overlapping. Okay? So what happens is fluorine's 2p orbitals overlap with krypton's 4p orbitals. Okay? And they overlap in a way that, like, krypton will let fluorine share space. Do you know why krypton will let fluorine share space? Because it's such a darn good tug-of-war player. What would you do if the world champion was in your midst? Would you pick up the rope? You wouldn't? Hold on. I'm sorry. If I took you outside and I said to you, we have the world's best tug-of-war player here today. Who wants to play against them? Are you telling me you wouldn't try? How many of you would be willing to play? Like, just for fun. Like, let's see how good this atom really is, right? Yes, that's what krypton does. Krypton's like, oh, you're like the best. Like, not really, but fluorine is so good at attracting those electrons that it's even talking krypton into sharing unnecessarily. Krypton doesn't need to share, but krypton is like fangirling around fluorine. Okay? Like, okay, yeah, we can share. You're like the best. I've heard about you. Okay, I'll pick up the rope. Doesn't need to. Yeah. But fluorine is, really hard to resist, if you will. Okay? Just like if I brought the world champion here, you would be curious, like, what makes this guy so good? Right? You'd pick up the rope, at least one of you, and then the rest of us would decide, yeah, no, I'm good, not playing against them. Right? So, but you would, and that's what happens. Okay? All right. What'd you do for oh, hold on. Let's talk formal charges. What's the formal charge on each fluorine? 0. What's the formal charge on krypton? 0. Because 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. What about BRF5? Well, what was the problem there? The 5 fluorines, right? Is there a step that says question the method? No. So did you draw what you were supposed to, whether you thought it was right or not? Yes. Okay. Here's what you should have drawn. Here's BRF5. Okay. What are the formal charges on everything? 0. Okay. Those are the correct structures. All right. Any questions on that piece of it? No? Okay. Do you want to talk molecular shape a little bit? Okay. What shape did you have for COCl2? Trigonal. Trigonal Rex. The T-Rex shape. Not quite. There's two trigonals. Do you remember? There's trigonal planar and there's trigonal pyramidal. Do you know what this one is? It is one of them. I'm not going to answer. Oh, P.S. I will tell you this. I think what I'm going to do for homework is I'm going to post something for you to use to determine shapes. And then I'm going to have you like relook at this. Okay. But here's what I will tell you. Okay. When you are determining shape, you regard a double bond as just one pair. Like, because the oxygen is pulling in one direction. It's one thing pulling in one direction, which is really what determines shape, like how many things are coming off the central atom. But by things, we're really talking about atoms. It's just that this atom is pulling a little bit harder than the other two because it has two ropes instead of one, right? But in reality, the shape is going to be the same whether it has two ropes or what. Does that make sense? So don't let double and triple bonds affect your choice of shape. Okay. All right. What about SF2? I hear linear and bent. Any other choices? How many of you said linear? How many of you said bent? Okay, well, you'll decide over homework. Okay. CO3 2 minus, trigonal something. It's actually going to be the same as COCl2, isn't it? It's really not phenomenally different, other than instead of having two Cl's, it has two more oxygens, right? Okay. SiCl4, did we get this one? Tetrahedral, very good. See, you know something. Okay. Tetrahedral. Why tetrahedral? Because there are four atoms coming off the central atom, right? Think of it as four sets of bonds. Okay, because I want you to think of this as how many sets of bonds? 3, because that'll inform your structure. Okay. I'm guessing you had no clue on KRF2. I'm not going to answer right now. Okay. And then any thoughts on BRF5? Hexa what? Hexahedral. Not a bad guess. You'll look at it for homework. Okay. How'd you do on polarity? No? All right, so that'll be where we start on Wednesday. Okay. Sounds good. So All right.